We start the recorder. And our next speaker is Professor Mishko Mitkovsky from Clemson University, who will speak on sampling, interpolation, and uncertainty. Please.
All right, thank you. So first, before I start with my talk, I would like to I would like to make sure that you all can hear me. I hope that works well. Second, I would like to thank the organizers for putting this wonderful semester. So I think it's really nice to have so many different topics which are all close to my heart in one semester. Today I actually want to try to speak on something more related to Poltoradsky's main lectures. However, unfortunately, I wasn't able to come up with something decent, and then I want to present half-baked things. So I decided last minute to talk about what was my main interest in the last couple of years, which is sampling results and connections with the uncertainty principle. The title of my talk is Sampling, Interpolation, and Uncertainty. So initially, I wanted to talk about some interpolation results as well, but unfortunately, putting the things together. When I was putting things together, I realized that I really won't have time to talk much about interpolation. So mainly, most of my talk will be mainly about sampling and its relation with the uncertainty principle. Okay, so I'm going to start with the Shannon sampling formula, which is the most famous, most well-known, and most applied, I guess, sampling result. In the same time, the simplest result. The Shannon sampling formula says that if you have a band-limited function f, so a function whose Fourier transform has a support in some fixed set. I mean, I just choose for convenience an interval from -1 to 1, so one-dimensional case. We know that such function can be recovered from its values. So it's not just it's uniquely determined, but can be recovered in a stable way from its values at half of the integers. So the formula is of course well known and it's given here. It should be. It's in its simplest form. We should think of this sum, of course, in the L2 sense. So it's an L2 convergence. This is just basically saying that complex exponentials with integer frequencies form an orthonormal basis in L2 -1 to 1. Just you apply a Fourier transform to that and we get this formula. And of course, the natural question now is, can we replace the sequence of integers with another sequence of real numbers? Or in other words, can we do, is irregular sampling possible? So what do we mean? Let's more precisely, let me say more precisely what sampling, what I mean by sampling. So a sequence is sampling for the in this setting for a Paley-Wiener space if the norm of any Paley-Wiener function is up to a constant equal to the little L2 norm of f evaluated at that sequence. And in that case, if that's the case, then we can find reconstruction formula, stable reconstruction formula, where now SNs are not necessarily these translations of the sinc function, but some maybe more complicated functions, but they exist. So now, when do we have which sequences are sampling? This is almost characterized by a classical result of Berling going back to the 40s, which says that a discrete sequence which satisfies this density condition is must be sampled. Well, of course, the density condition, I mean, this lower Berling density just means you take your sequence, you take an interval of size, let's say R, and you see how many points of that of your sequence lambda belong in this interval. You move the interval along every by just moving the center, and then you divide it how many integers are in this interval. So you basically comparing lambda with the sequence of integers. We are looking at the place where this is the smallest, and then take a limit. I mean, you can take limits, but that turns out it turns out that this limit exists. So if this is greater than 2, then we are sure that this will be a sampling sequence by this result of Berling. This density condition is almost sharp, so almost necessary as well. Namely, if you want lambda to be a simple sampling sequence, we must have that the density must be greater or equal to 2. And for example, the most classical result, the Shannon sampling formula is actually about sequences with density exactly equal to 2. But this this case, when the density equals 2, is more subtle, and yeah, there are some if and only if conditions, but they're not as as I guess transparent. It's easy to check if this Berling sufficient condition. Sorry. Now, the necessary density condition holds also in higher dimensions. So if you look at a Paley-Wiener space in the dimension D, where you assume that the Fourier transform is, so Paley-Wiener space of functions whose Fourier transform is contained in a D-dimensional cube, and we still have the same result, the same necessary result about density. This is a famous result of Landau from the 60s. However, there is no sufficiency condition of similar kind, which can be easily shown by, it's not that we don't know it, but there is no, one cannot find such a condition in general, such a simple condition. Sampling concept, the concept of sampling can be naturally defined in general reproducing kernel Hilbert spaces, and similar density results can be proved in the context, in this more general context, for example, in the context of Bergman spaces, Bartman-Fock spaces, and so on, weighted versions of these spaces. These are due to Saib, Ortega, Cerda, and their collaborators. But I'm not going to talk about these results, even though they are closely connected. So now the question is, can we sample using non-discrete measures? So can we define a concept of sampling which is not going to use points? So a measure mu on RD, so let's define this in the higher dimensional case right away, is called a sampling measure if basically this sampling inequalities. So here, by this, I just mean inequalities from above and below up to a constant, which doesn't depend on F, of course. So we would like these inequalities to hold for any F in the Paley-Wiener space. In that case, we say that the measure mu is sampling. So if mu is just sum of discrete Dirac point masses, then of course we are back to the classical sampling definition. again, if you have such an inequalities, so if you have a sampling measure, then we can reconstruct our function by this type of formula, the same type of formula. And of course, the most classical case of a sampling measure, besides the one that the discrete case that we just discussed, is the case when we look for a sampling measure of the form some indicator of a given set and the Lebesgue measure. So, so basically, we would like this inequalities where you put a set here, E, and then you put the Lebesgue measure. Of course, the upper inequality is trivially true, but the lower inequality is the interesting part. And that is what will allow us to have a reconstruction formula like this. And of course, this is again a classical problem which was solved in the 70s by Logvinenko, Sereda, and I think Lipanea, whose results were in the proved in the 60s, a little bit earlier, but for some reason it's mostly Logvinenko and Sereda whose name is attached to this solution. Just a measure of this form is called the sampling measure. Well, not is called, but is the sampling measure in this sense, right? If and only if the set E is relatively dense, which means that basically this is the condition that there exists some constant positive and some scale R, such that for any ball of radius R, if you intersect your set E by this ball, a big portion of the measure of the ball will actually be in the set. So it's dense everywhere in this sense. Now the question that I was interested in is the more recent concept of mobile sampling, which was introduced quite recently, actually, in the last, I think, 10 years ago by Unikrishnan and Vetterli. These two are actually engineers, not mathematicians doing engineering. They're actually engineers that got interested in this problem from a practical standpoint. So they asked, can we sample along a lower dimensional surface? And actually they were mostly interested in sampling along curves in their work, but very soon even themselves started to actually try to extend this to other surfaces. So there was a lot of research in the last few years on this problem of mobile sampling. Several results, notable results by Jose Luis Romero, Groshenik, Ulyanovsky, Zlotnikov, and others, which actually were asking, can we sample? So what will happen if our set of points along which we sample lies on a curve, or what if we sample along that curve? And the typical feature of all these results is that it's somehow they're all one-dimensional because all these curves have some kind of one-dimensional flavor to them. And they mostly prove necessary results, which I think, I don't know, from practical perspective, are, I guess, not that important. So it's the sufficiency result that we really would like to have, to know when can we sample, right? When can we have a stable reconstruction? So let me explain this, introduce this in a more precise term. So the mobile sampling problem is basically concerned about the intermediate case for a given K, which is, you should think of it as a dimension between the dimension of the space B and 0. And actually K can be between P equal to 0 and B, although that's already covered by the classical results, as I will explain in a second. When is the measure of this form now, where I use the K-dimensional Hausdorff measure? When is this a sampling measure for this D-dimensional Paley-Wiener space? And as you can notice, if K equals 0, so if you use the zero-dimensional Hausdorff measure, this is just the Berling, the classical Berling sampling problem. And if K equals D, that's the Logvinenko-Sereda-Panea problem. So in these cases, the problem is essentially solved. And the question is, what can we say something in the intermediate case when K is between 0 and D? So in a sense, when we have a lower dimensional surface. So as you saw the classical results of Berling and Logvinenko-Sereda, of course, suggest that one defines the following concept, which is called a lower surface density. This was actually introduced by Vetterli when they actually talked about mobile sampling. So they themselves introduced the concept of surface density. I think they called it path density because they mainly, they were mostly interested in the case with K equals 1 and D equals 2. But I think in general, the surface density makes a little bit more sense. It doesn't really, it's not important. This is their density. So you basically use the Hausdorff, K-dimensional Hausdorff measure in place of the counting function or the Lebesgue measure in the Panea-Logvinenko-Sereda case. And of course, we would like to say, is it possible to give a sufficient condition on gamma in terms of this density, which will guarantee sampling? So the result that I mentioned before of Romero, Groshenik, Ulyanovsky, Zlotnikov, they all actually are results which guarantee, which show that if gamma is a part of some regular surface with one-dimensional features, then a necessary condition for sampling is that this lower density is greater or equal than some fixed constant, which depends, of course, on the surface. So what in a joint work with Ben Jay this year, but beginning of this year, we were able actually to get a sufficient condition of Berling type by assuming a very mild regularity of the surface. So let me not go into that, but it's a very mild condition which just takes out some very pathological cases. And under those mild conditions, we actually found a density condition which guarantees sampling. Now, omega D, as usual, denotes the Hausdorff measure of a D-dimensional ball, unit ball. Remember, D is the space, the Paley-Wiener space where we are, the dimension of the Paley-Wiener space that we work in. So if the lower Berling density, well, the lower surface density, this one, is greater than this fixed constant, depending only on the dimension, then we have a sampling, then gamma is sampling of the minus 1 size. So we are actually giving a sufficient condition for sampling for codimension 1 surfaces. So codimension 1 surfaces only. And we believe that for lower dimensional surfaces, this type of result is not possible. Okay, so let me explain. Oh, by the way, of course, the sharpness. I want to say that unfortunately there is no way to get a necessary condition of a similar type, and Groshnik and Jose Luis Romero proved in joint work with Unikrishnan and Vetterle proved that the best that one can say about the lower surface density of a sampling sequence is that it must be positive. So it must be greater than 0, but you can get anything as close to 0 as you want. So you can get sampling sequences which have lower density as close to 0 as we want. So there is no necessary condition of this type. It's not possible. We only have a sufficiency condition, but our result is almost sharp still in certain sense. Namely, we can show that if you replace this by d over 2, so basically if we can get rid of this 3, then we were able to find a surface with density this times d over 2, so which is not sampling. So our result has the right dependence on d, except for this coefficient 3. So the power dependence on d is asymptotically correct. I think it's really gonna boil down to just constructing a little bit more a cleverer counterexample, but the result is essentially sharp. Okay, so what is the main idea behind this result? Behind the proof of our result? Namely, we use a Burling, the classical Burling idea. We use the compactness argument that even that he suggested when he proved his sampling result. However, the difficulty here is that there are no results about 0 sets of Paley-Wiener functions in the higher dimensions, which are of the same strength as in the one-dimensional case. So so the main really result that we needed to be proved is the following. So if we have a Paley-Wiener type function, so we have a function whose Fourier transform is supported in a d-dimensional unit pole. So this should be a d-dimensional unit pole. And assume that this is bounded by 1 and it's bounded by, this 1/2 is of course not important, just bounded to below, bounded away from 0 at the point 0. Then we have the following estimate for the 0 set. So this actually should be a Hausdorff measure, not that age. So we have the following estimate for the 0 set of such a function. Results of this type were obtained earlier by Ronkin in the 70s and by Donnelly and Pfefferman when they worked on the nodal sets of the size of the nodal sets of eigenfunctions of the Laplacian. So the idea that we use is similar in spirit. Namely, we just estimate the size on each d minus one dimensional slice, and then we average this estimate. Of course, there are many subtleties in between technicalities, but that's the main idea. And then when you get this estimate, the next step is to actually get a fuzzy version of this estimate. Namely, instead of estimating just the zero set of our function of Paley-Wiener type, we want to estimate this slice. So just to extend our estimate to a little bit bigger set, but of course we have to intersect with some d minus one dimensional surface, so that, again, this is the d minus one dimensional Hausdorff measure is not infinite, right? So if this doesn't exist, then obviously we get infinity. There's no way to get such an estimate. But you see, it's again the same type, and there is a lim sup missing here. There should be a lim sup. Somehow it got away. I think it got cut off because the formula is not fitting. So basically the same type of result holds, and this can be obtained by some kind of compactness argument. So it's not that bad. All right, so combining these two results, one can actually, one gets the sampling result that I mentioned last time, in the last slide. So these are the two main ideas and ingredients of the proof. So now I want to mention a similar type of result that Ben and I obtained a little bit earlier, which was so of similar spirit, required slightly different approach, and it concerned about it concerned functions which are not just band limited from above, but also they are also band limited from below. So basically, their Fourier transform is supported in an annulus of a fixed width. Let me say more precisely what I mean by this. So suppose that we have we have RD, that's our frequency space, and suppose that we have some C1 smooth compact D minus K dimensional submanifold of RD. So let's think of, for example, let's say that you have R3, and then sigma could be a two-dimensional circle, well, one-dimensional circle. And then you just take, for a fixed width, beta equals some beta greater than 0, we take a beta neighborhood of that sigma. So if you have this circle, and then you take a beta neighborhood, basically you get some kind of torus, a donut, right? And we assume that we are looking for, we are working with functions whose Fourier transform is supported in that donut. Another probably more natural thing is to take sigma. So if you're in if b equals 3, to take sigma to be a two-dimensional sphere. And then in that case, you basically have a shell around that sphere of size beta, with beta, and then you can assume the Fourier transform is supported in that shell, which is a three-dimensional version of the annulus. Of course, you can take K to be equals D, or sigma, in which case sigma is a zero-dimensional submanifold, like a point. In that case, of course, if sigma is a point, if you take a beta neighborhood of a point, you will get the three-dimensional ball, and that actually covers the usual Paley-Wiener space, and then the Fourier transform will be supported in a ball. Okay, so we have this slightly more precise, more restricted Paley-Wiener space of functions, and we are interested in studying again sampling sets in such in such spaces. And I will actually explain why such results are useful slightly later. So I guess, as I said, we are interested in the sampling problem for functions in this more restricted P-Leviner space. And here, again, there is a notion of relative density or some kind of density which plays a role. So here, the right condition is the so-called geometric control condition, which is, of course, a well-known famous condition from control theory, which was introduced by Bardos, Lebeau, and Rauch in the 70s, I guess, again, which is basically a one-dimensional version of relative density, namely a set. This should be D, but it doesn't matter really. So we have a set E in RD. We say that it satisfies the geometric control condition, or GCC, if there exists a scale R and a fixed positive constant, this C, such that for any line segment of length R, the one-dimensional Hausdorff measure of the intersection of E with this line segment is greater or equal to C. Of course, this can be generalized to any dimension between 1 and T in a very similar, in a straightforward way. So we define K geometric control condition by just using, instead of line segments like this one, we use K-dimensional cubes or K-dimensional balls with size R, of scale R. And basically, again, require the same type of condition, replacing this with a K-dimensional Hausdorff measure. So you get the corresponding geometric control condition. And of course, notice that the usual relative density, Paneello-Gulenko-Sereda relative density, is just obtained when K equals N. So this is just the classical relative density. So we need these refinements of relative density to prove the sampling result for the for P-Leviner spaces of an annulus. That's how I mean, the annulus is what we were initially interested in, and that's how I want to describe this theorem. So again, so we have a P-Leviner space consisting of functions whose Fourier support is contained in some better neighborhood of some C1 smooth n minus k dimensional submanifold of R in RD in the previous. It doesn't really matter. So now, which sets E are sampling sets? If we have a set E which satisfies the K geometric control condition, where K is just this. So if we have codimension K surface sigma, then we have to use the K geometric control condition to have sampling. As you might guess, this is of course natural. Just having in mind the classical Gulenko-Sereda. And we get this result. The important thing, there are two important things. So for our applications, the main thing was this constant C. You see there is this R which appears here. So it's not just a neighborhood or a better neighborhood of sigma, but what I mean here by R sigma is just dilation of sigma by a factor of R. So we take sigma. So for example, in the case when sigma is just a circle, unit circle, you just dilate, you make it a circle with radius R, but you're not changing beta. So the width of the annulus is the same. We just make the radius as large as we want. And the important thing is that this constant, the sampling constant here does not depend on R. So what we get, of course, if you want to use the whole ball, just as in the classical case, then this constant will depend on R and actually depends exponentially on R. However, if you look at the annulus only, it's independent on R, and that's the crucial thing when you do applications, it turns out. Okay, another thing which is not that nice for us is that we actually require to take this E delta represents delta neighborhood of our set E. So in the classical Loguenenko-Sereda-Panea result, there is no such neighborhood. We had to take a neighborhood because our proof doesn't work otherwise. But we don't know actually whether this can be removed. So it's an open question whether we can remove this delta. Okay. So now let me try to explain the applications of these results. To do this, let me first go back to the most basic form of the uncertainty principle. So why sampling an uncertainty principle? So I will try to explain this, and I will try to explain how these sampling inequalities can be applied to some basic problems from control and stabilization theory in PDEs. So the informal form of the sampling of the uncertainty principle is that harmonic analysis, harmonic analysts use is that a non-zero function and its Fourier transform cannot be simultaneously small in some sense. Of course, this is not a precise statement. The most classical form of the uncertainty principle was obtained by Wiener in 1925 in his Göttingen lectures, where he formulated the uncertainty principle as an inequality of this form, which of course can be interpreted as a statement that G, so L2 function G and its Fourier transform cannot be simultaneously concentrated around a single point, no matter which point you take. Okay, so that's what I said. Heisenberg, a year later, formulated his version of the uncertainty principle, the most famous one, saying that a position in the momentum of a quantum particle cannot be measured simultaneously. And actually, mathematically, this statement is exactly equivalent to the Wiener statement that I just mentioned above. Operator theoretic formulation of this uncertainty principle is that in some sense, the differentiation operator and the multiplication operators are strongly non-commutative, namely they satisfy this. Actually, it's an identity, and C is a complex number which you can compute. I just was lazy and didn't compute it. I wrote this in this form as an inequality just to stress that most of the results actually require this inequality only. So if you have such a thing for two operators, there some non-commutativity of this sort, then you will get some uncertainty inequality of Wiener type. Paul Dirac, his famous statement that non-commutativity of the form above is the most distinguished feature of quantum theory, at least the mathematical part of quantum theory, tells us that the uncertainty principle is one of the central principles in quantum theory. So the operator theoretic formulation of the inequality of Wiener's inequality that I mentioned in the previous slide is this form, which again can be viewed as some kind of concentration result, but also it can be viewed that as a result saying that an element of L2 cannot have, two operators which are non-commuting, like differentiation and multiplication, cannot have the same eigenvector. Of course, that's trivially true, but this is a quantitative version of this impossibility of non-commuting subadjoint operators to have a common eigenvector, so they cannot even common approximate eigenvector in some sense. So everything is governed by this fixed constant here. Okay, so try to remember this inequality, because you will see that this inequality will appear later in our connection with these problems that I mentioned about sampling and about applications to stability and control. So now, just a natural question is, does there exist an orthonormal basis consisting of common approximate eigenvectors of the multiplication operator X and the differentiation operator D, which almost diagonalizes both of them? So that's a natural question because, of course, all PDEs are combinations of X and D, and we would like to find a basis, a common basis to study them, to diagonalize or almost diagonalize them. So the same question can be reformulated as a question: can we find a coordinate system which is suitable to study both X and D simultaneously? And it's interesting that one can actually obtain, it's a simple result that can be obtained that basically says that that's impossible in a very strong sense. So namely, if we have an orthonormal basis, Fn, let's say, which almost diagonalize says both X and D simultaneously in this quite weak sense, I would say. So we would like the matrices of these two operators in the same orthonormal basis to be almost diagonal, but almost diagonal in a very weak sense, as you see. So you want all diagonal terms to weakly go to zero. And if we want these FENs to be somehow common eigenvectors of this weak type, so we don't require these to be, this left-hand side to be zero, just we want that to be less than infinity. So a very weak type of common eigenvector, I guess. Still, this is impossible. So even if you very drastically relax the the simultaneous diagonalization, you still cannot do it. And the consequences of our result, which was obtained with my student Audun Lee, is the classical Balian law theorem, saying that the Gabor system, the classical Gabor system consisting of translations and modulations of Gaussian, cannot, so not just a Gaussian, sorry, of any L2 window function. If we have an orthonormal basis, then that the window function cannot be localized both in the space and in frequency in a very strong sense, like this. That's the classical Balian law theorem. Another result that can be obtained as a consequence of our is the much stronger result of Groshenik and Malinnikova, which actually relaxes this Balian law theorem and allows G to be actually a sequence, an orthonormal basis, and then again they obtained a very strong non-localization condition that must hold for G in order to be an orthonormal basis. And both of them are consequences of that simple result that I just mentioned. Okay, so let me go to what I wanted to talk about, the control theory and stabilization of PDEs, of course, a very classical subject. Given two self-adjoint operators, so think of A as being differentiation operator like a Laplacian, and R sigma, again, it's a general self-adjoint operator, but think of it as some kind of restriction operator, so multiplication by some indicator of a set. So, and consider this differential equation. And the main question in control theory, at least of this type, is the question whether if we start with some initial state, can we choose F here to drive our system from U0 to any other state U1 that we want. So can we control our evolution, this evolution by controlling it on a subset sigma. So sigma is some subset. And of course, we would like sigma to be as small as possible and still to be able to control it. The important thing here to remember is that this A, the differentiation operator, and this R sigma are basically a multiplication operator, right? And they also, they kind of have a non-commutativity relation between themselves. Traditional way to establish controllability is to prove the corresponding observability inequality. This is the so-called HUM method, or Hilbert uniqueness method of Lyon's. Using this, one can actually formulate an equivalent version of the observability inequality, which is important for us, because as you see, observability inequality, which guarantees it's basically equivalent to controllability, is this inequality, which should remind you of the usual uncertainty principle. Before we had the B minus mu or operator here, but again, the main thing is that A and this operator, so this is a differentiation, this is a multiplication operator. So their non-commutativity is the reason why this inequality holds. Another thing, and the connection to sampling problems comes again from this type of inequalities, namely if A is some kind of differentiation operator, then if you want to make this small, you want to require this function. So if you take, of course, a Fourier transform here, we want the function to be to have a Fourier transform supported in some neighborhood of lambda, and this should be true for every lambda. So this should, so you should think of lambda as this R, the radius R that can change, and we want to look at annuli, and we want this inequality to be true. So this C to be in the perfect case scenario independent of lambda, or to depend on lambda in a way that we can still get a useful inequality. And of course, if you make this very small by requiring that Paley-Wiener type of assumption, what you want to prove in order to explain, to study controllability or observability is a sampling inequality, which is just this is greater or equal to this. This is just a sampling inequality in disguise. So sampling inequalities are very closely connected to observability and controllability of PDEs. And therefore, we were able to obtain some interesting results using our the result that I previously mentioned that we proved about sampling. Okay, so stabilization, another problem. So before I actually went completely abstract, now I decided to do completely concrete. So let's say consider a Klein-Gordon equation, one-dimensional. Of course, we have a damping term here, which is this one. So if gamma is no, if there's no damping, then the energy of the solution of this Klein-Gordon equation is well known to be preserved, to be constant. If we have a positive, if gamma is a positive constant, then the energy of the solution has exponential decay in time. Of course, this can be generalized in a much more general semi-groups of equations. The natural question is, under what condition on the damping term we can guarantee an exponential decay? So let's say gamma is not a constant, fixed constant, and maybe it's positive some on just on a part of our domain, just like in the control, right? So we would like to find the smallest possible sigma that will allow us exponential stabilization. So a complete solution to this one-dimensional problem was provided very recently, surprisingly, in 2017 by Stanislavova and Malki, which actually says that exponential decay is possible if and only if this set, so the set where gamma is bigger than a fixed constant, is relatively dense. So that reminds us of Bogdanenko-Sereda. And the same question can be asked if you replace this with a fractional, so the Laplacian with a fractional Laplacian. And Malki and Stanislavova were able to obtain a result which is not, unfortunately, sharp. And then in 2018, my student Walton Green, using techniques from uncertainty principle, actually was able to improve their result and prove that the same relative density condition is also, again, sufficient for stabilization. The higher dimensional version of this result was obtained by Burke and Joly using methods from semi-classical and micro-local analysis. And then together with Bolton and BNJ, we were able to use uncertainty principle approach, which comes into play very easily if one uses this well-known results from semi-group theory, Gerhard Prus or Borychev-Tomilov. One can transform the stabilization problems into inequalities of this type, which is just an uncertainty principle as before. So one needs to just prove a corresponding uncertainty principle and sampling inequality to be able to deduce stabilization. And that's what we did. And that's how this Paley-Wiener theorem for the annulus was discovered, which was surprisingly not known before. Okay, so I see that I don't have time now. I'm out of time, so I'm gonna skip my last part and leave room in time for questions. So thank you.
Thank you very much. Questions, comments? So
yes.
Yeah, go ahead.
I have a question. So, okay, my first question is your C in your theorem depending polynomially or on your density?
In which?
In your two theorem, you obtain the.
Yeah, let me just the one for the annulus.
Yeah, in the annulus, yeah. And the first one you proved.
Okay. Yeah, let me try to get back to them. So polynomial in so this C here, if you're asking about this C doesn't. The main thing is that it doesn't depend on R at all. So it just depends on the width of the annulus, not on the radius. And that's what is important in this application that I mentioned.
Yes, but you have your KGCC condition. So you have a kind of density. Yes. So yes. I think that your C is depending on your density. And
oh, that density, yeah, I don't remember. Yeah, that's a good question. I don't remember. Yeah, I think so. So what we use is basically a result for the strip. And there, if you use this more precise reasoning of Kovrishkin, I think one can get polynomial. And I'm not sure if we did that or not, but yeah, I think one can get polynomial dependence. But yeah, I'm not, I don't remember right now.
Okay, thank you. Because in the result of Kovrishkin, the polynomial dependence is essential for apply for some application in control theory. So it's
yeah. I think one can get. I think whatever he gets, we get here because we use that result as a step toward the solution.
Okay.
So I think one can get.
Okay, thank you. And my second question would be, what's the theorem expected for example, the Paley-Wiener space on a cube? Do you think that the KGCC condition is sufficient to have?
So you just general, just the classical Paley-Wiener?
Yeah, On the classical polylinear, yeah.
I don't. Well, of course, if k equals the dimension, then that's true, right? But in general, I don't think it's gonna be sufficient. But that's, yeah, I don't know actually. I'm not sure. That's a good question. I don't know. I don't think so. But, yeah, if we don't assume an annulus, I don't think it will be sufficient. That's my feeling.
Okay. Okay. So there is no chance to reduce delta to 0 on the classical polylinear space.
Yeah. No. Well, for our proof, will not work. And okay. I think it's not true, but I'm not sure.
Okay, thank you.
Mm-hmm.
Other questions? There is a question in chat asking if you could please share your slides.
Oh, sure. Share where?
You can do it in chat. There is in the right bottom corner, there is like a smiley face, and next to it there is the icon of a document. Okay, if you can open, if you can click chat.
Yeah.
All right.
Yes.
Okay, so that is actually less trivial. Maybe you can click this tab here to chat.
I mean, I'm fine to share it on the web page, to post them on the web page so that everyone can. I don't know if there is a way to do that. Let me see if I can do this. Okay, so let me try.
I actually don't see how to do it. You know, but maybe you can send it via email to one of us, to me, to Ilya, or to Javad, and we will share it later today or tomorrow.
Yeah, that will be the easiest. Sure, I can do it.
Well, thank you very much. So, are there any other questions? If not, then let's thank our speaker once again.